Okay, this is going to be our fourth and final video on our, in our series of electric flux and Gauss's law. And so in this video, we're pretty much just going to be discussing some of the results of Gauss's law that we can sort of get by using Gauss's law on solid conductors. Okay, so we're going to be looking at solid chunks of conducting material, applying Gauss's law to it, and some of the things that we talked about before, and sort of seeing what results we can get from that. So we're going to start off by looking at this image that we have here. We have three different sort of configurations for this conductor. Excuse me. And so let's start off. So we've already seen that for a conductor in equilibrium, the electric field has to be zero at every point inside that conductor. And so any charge any excess charge that is on that conductor has to be sitting on the surface. We already talked about this last video, right? So let's take a look at case A here, where we have the first picture in this this diagram. We have a solid chunk of conducting material. We have some excess charge QC on the conductor, and what happens? Well, exactly what we would sort of expect, what we've already talked about. The charge all migrates to the surface, right? What if we take this conductor and then we clear out a cavity in the center of the conductor? We might wonder, should we expect to see the charge, this QC, distributing itself around the surface of this inside cavity? And we can kind of answer that question by using Gauss's law. If we wrap the inner cavity in a Gaussian surface, and we take a look at the charge enclosed in this Gaussian surface, we can see that the charge enclosed has to be zero, or the net charge enclosed has to be zero. And why is that? Because if that wasn't the case, then we would see that at the surface, if there was some net charge in here, Gauss's law would tell us that at this surface there would have to be some electric flux, which means some electric field at that point. And we know there can't be an electric field at that point. So what does this tell us? This tells us that if we have a cavity which is empty, right, there's no charge in the cavity, then no charge will build up on the edge of the inner cavity, because that would result in an electric field. And so still we have all of our excess charge building up on the outer edge of the conductor, right? But now, what if we put a charge inside our inner cavity here? What's going to happen in this case? Well, by the same logic, if we wrap the inner cavity in a Gaussian surface, we can see that if these charges here didn't migrate, we would have a net positive charge inside, and we would end up with an electric field at our Gaussian surface again. So clearly that can't happen. So what ends up happening is this positive charge that we've put inside the cavity induces a negative charge on the inner surface, on this surface that's the boundary between the cavity and the conductor. So it induces this net negative charge, and so now when we wrap this conglomeration of negative charge that's been induced in our conductor, and the positive charge sitting at the center of our cavity, we again have no net charge inside our Gaussian surface, right? Because the positive charge and the negative charge cancel out, and we again have no electric field in our conductor as it has to be. But because we've pulled more negative charge into the center of the conductor here, we end up with additional positive charge on the outside of the conductor, right? We've pulled more negative charge in, so some positive charge has to sort of migrate to the surface. And so we're going to find that the positive charge at the surface is the QC that we had before, right? Plus whatever the value for Q is, this positive conductor in our cavity. Why is that? Because the positive conductor in the cavity has a value of Q, has a magnitude of positive Q, and so it induces a total value of negative Q charge building up on the inner surface of the conductor here, the the sort of boundary between the conductor and the cavity, and so we need to compensate for this negative Q that's been sort of pulled out of the conductor, and so we get a positive Q on the surface. So we end up with QC plus Q on the outer surface, and that's sort of how the charges will arrange themselves here. Okay, and so those are sort of three interesting results that we can get from looking at sort of Gauss's law inside a conductor with a cavity now, right? We're going to take a look at a quick example here. This is a pretty simple example, but still I think good to look at. It's basically just the setup that we saw above, but with some numbers here. And so what do we have here? We have a conductor with a cavity, carries a total charge of plus 7 nanocoulombs. Within the cavity, insulated from the conductor, is a point charge of minus 5 nanocoulombs. How much charge is on the surface, both the inner and outer surface of the conductor? So, I mean, they only have sort of one picture drawn here, but we can kind of imagine it like before, right? So imagine we just had our conductor. I'll draw them here. So this is like the outer surface of our conductor. This is like the inner surface of our conductor. And let's say we started off with no charge in the center, and this thing had a net charge of plus 7 nanocoulombs. I'll take each one of my pluses here to be like 1 nanocoulomb. So we'd have like 7 pluses, 3, 4, 5, 6, 7 along the outside, right? So now we plop a point charge of minus 5 nanocoulombs in the center, right? So this is like the second diagram here, and we plop a minus 5. That's hard to see, but imagine. Okay, maybe that's not great. A minus 5 nanocoulomb charge in the center here, right? So what has to happen? Well, the charge in our conductor has to rearrange itself so that when we draw this Gaussian surface that we see here, that it is able to encompass no net charge, right? So we have minus 5 in the center, so we need plus 5 kind of building up along the inner surface here, right? So now when we wrap this thing in a Gaussian surface, and I won't try to draw it here, but you can see it here, we now have this setup. So we have we have negative 5 nanocoulombs in the cavity. We have 5 nanocoulombs building up on the inner surface. When we wrap this whole thing in our Gaussian surface, there's no net charge inside it, and so no net electric field inside the conductor. And what's left over? Well, we end up with still 2 nanocoulombs on the outer surface, right? We still have 2 nanocoulombs that remain on the outer surface because they didn't need to get pulled to the inside. Now, what if instead we had put a larger charge, and that's not really part of this problem, but we can kind of just play with it. Let's say instead we had dumped a charge of negative 10 nanocoulombs inside. Well, what would need to happen? So let's take a look. So we have our conducting surface. Well, the outer surface of our conductor. We have the inner surface of our conductor here. Let's say we put that negative 10 nanocoulomb charge in here. Well, then we would need a positive 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. So we would need a total positive charge of 10 nanocoulombs building up on this inner surface, so that when we did wrap this in a Gaussian surface, the net in charge enclosed is still 0, and we have no electric field being induced inside our conductor. But we only had a positive charge of 7 nanocoulombs here, so we need to pull an additional 3 nanocoulombs, positive 3 nanocoulombs from the conductor. So that means that we have a net negative 3 nanocoulombs remaining. So we have a negative 3 nanocoulombs building up on our surface here, right? And this is because we have to keep the total charge in the conductor conserved, right? We can't just be creating charge from nowhere. So everywhere that we pull a positive charge, like every time we pull a positive charge to this inner surface, a negative charge has to build up on the outer surface, okay? And that's sort of how we would handle problems like these, okay? I guess I left this large area for a solution, but I pretty much discussed it all up here. So I'll just skip over this portion, and we'll head down here. So another sort of important consequence of Gauss's law is that electric charges, and so electric fields outside of the conductor, have no effect on the interior of the conductor. And we can see that in the two diagrams we have set up over here. I'll talk about B in a second, but we can kind of see what happens in A here. So let's say we have this yellow sort of square thing is meant to be some sort of a conductor, right? So we have a conductor with no net charge put into a strong electric field here. And so what happens? Would we expect to see electric field inside the conductor? Well, no, we can't really see electric field inside the conductor, because if we wrap this in a Gaussian surface, there would be no net charge inside, right? And so we would expect to see no electric field at the surface, but we're also going to see no net charge inside because there's nowhere for these electric field lines to begin and terminate. So what kind of ends up happening? We have this conducting square that we plop into the electric field. It has no net charge, but in the electric field, what ends up happening is there's a negative charge induced in the side of the electric field coming into into our conducting surface here, right? Because we know that our electric field lines have to terminate on negative charges, and so we end up inducing a bunch of negative charge over here, and because of that, a bunch of positive charge is induced on this side, which is where the electric field lines will originate from and continue in this direction. So we kind of end up with this setup here. We're gonna discuss some of these ideas more in chapter 23, but basically this is what we end up seeing if we put a conducting, I guess, ring or square in this case inside an electric field. We expect to see no electric field inside the cavity of the conductor, but we do expect to see the electric field outside, and it'll terminate and start on the surface of this conducting surface, right? And so I guess I can talk about this picture first. So what do we kind of end up seeing is that we have a very sort of safe region inside these conducting surfaces, right? And this is a Faraday cage that we see here, and we see this guy standing inside this this sort of metallic box, and although there's a bunch of charge outside, right? We see this very powerful sort of arc generated here, and the person inside is totally safe because there is no electric field, there is no charge inside the box, right? So that's just another interesting sort of result from Gauss's law that we can sort of get at. The last thing I want to say about Gauss's law and sort of how it pertains to conductors and what's going on inside these conductors is that we see that all of our electric field lines in this case here, and again, we're going to discuss this more in chapter 3, or 23 I should say, we can see that all of the electric field lines here originate perpendicular to the surface, right? And we're going to see why that is a little more in chapter 23, but for now, we can use Gauss's law to calculate the sort of relationship between the electric field and the charge density at the surface. And this actually, I just saw a typo. This should actually be the magnitude of the electric field, because we just talked about how it's going to be perpendicular to the surface, but we're now going to talk about the relationship between sigma, which is our charge density at the surface of our conductor, and the magnitude of the electric field at that point, because we already know about its direction, right? We just said it was perpendicular to the surface. And so how does this kind of work? So we've already looked at the electric field outside of an infinite charged plane, right? We looked at that last video. It was the last problem we looked at. And in that video, maybe I'll come back to this result in 1 second. So in that video, we saw I'm going to kind of try and draw it here. We had set up a Gaussian surface, and this is like a plane here, imagine. Okay, so let's say this is our plane, and we had a Gaussian surface that was penetrating the plane like this, and let's say there was a bunch of positive charge on our plane here, and we saw that we had electric field lines emerging like this, and we were able to calculate what the electric field would look like there, right? So now imagine in this picture what we have here is this is supposed to be the surface of some sort of a large chunk of conductor, right, with some net positive charge on it that we can see here. So this side of our Gaussian surface is embedded in the conductor, right? Imagine this is like some big chunk of conductor, right? And so this is inside the conductor, and so we know there can be no electric field emerging from here, right? The only place that the electric field can be emerging from is from the surface going outward, right? And because of that, so now let's think back to how we did the problem, this problem of the infinite plane before, right? Maybe I'll do that. Maybe I'll do that down here. So the way we did the problem for the infinite plane was keeping this image in mind here, and we ended up labeling this outer surface S1, this inner this other surface S2, and this back surface here was S3. Okay, and if you guys don't remember this too well, just look at the last video because I'm going to be going over it kind of quickly here, but you can get more details in the previous video. We ended up setting it up so that the surface integral over all three of those surfaces of E dot dA, we broke that up into three different sections, right? We had the integral over section 1, E dot dA. Then we had the integral over section 2, E dot dA. And we had the integral over section 3, E dot dA. Okay? And we saw that this section, I'm not going to go over the whole thing again, but we saw that this section here was going to end up being 0 because dA was perpendicular to E. And we saw that we had to count basically this section twice because these were both equal, right? So we ended up with a situation where we had this thing ending up being something like, well, when we did the integral, it was like EA plus 0 from this thing plus EA, right? And so we ended up with 2 EA was equal to the charge enclosed over epsilon naught. But here there's going to be a difference, right? Where here we had to be careful because we had to go over both of these surfaces to do both surface integrals. There's going to be no electric field emerging from this side of the of our Gaussian surface because it's embedded in the conducting material, right? And so because of that, let's say in this case we labeled this one surface 3, let's say, and oops, that shouldn't be a C, that should be a 3, and let's say we labeled this no, don't draw it like that. Let's say we did it like this. We call this sort of curved surface here surface 2 as we did before, and this was surface 1. Okay, and so now we have no flux through surface 2 or surface 3, and so this term goes away, right? This term that used to have some value when we were looking at a charged plane, an infinitely sort of thin charged plane, now that we're looking at the surface of a conducting chunk of material, this one goes to 0, and so we lose this factor of 2, right? And because we lose that factor of 2, and we can kind of see what we ended up doing before, right? We wrote that our charge enclosed. This is all stuff that we went over in the previous video, but we wrote that our charge enclosed was actually equal to QA, or sorry, the Q was equal to sigma A, I should say. And so we made that replacement. And in this case, now since we've killed off this factor of 2, we're going to end up with EA is equal to sigma A over epsilon naught. These A's cancel, and we end up with E is equal to sigma epsilon naught. Okay, and this is the result that we end up finding for the magnitude of the electric field at the the surface of some sort of a conductor with surface charge density sigma. Okay, so this is an important sort of equation that we want to keep in mind, and we can use this equation in the example that I'm going to do just below here. Okay, this is kind of a simple example, but still kind of fun, and you know, just good to go over. So what do we have here? This is example 22.12 from the text, and we're looking at the electric field of the Earth. Okay, so the Earth is a conductor. It has significant sort of metal content. It is considered a conductor. It has a, I mean, okay, so I don't want to misrepresent sort of how the Earth is set up, but for this problem, we'll approximate it well as a conductor. Not every part of the Earth conducts, but overall the Earth is considered a conductor. It has a net electric charge. This electric charge results in an electric field near the surface of the Earth of 150 newtons per coulomb, directed toward the center of the Earth. Right. So we have our Earth, and we're going to have an electric field that looks like that, where the magnitude of the electric field is equal to 150 newtons per coulomb. Okay, and so we want to know what is the corresponding surface charge density, and then what the total charge of the Earth is. And so the calculations are pretty simple, but like I said, kind of fun, and so we'll go through them. So for part A, we have, well, we start off with the equation that we have above. So I'll just write this, and I mean this is really the same thing as this, because we know that the portion of the electric field perpendicular to our surface is really the magnitude, because like we talked about before, from a conducting surface, the electric field is always going to be perpendicular to the surface, right? And more to come on that in chapter 23. But this is basically the same as saying this, right? So let's just rearrange this equation slightly to give us this. And at this point, it's really just a matter of substituting in numbers, right? So we need to substitute in for epsilon naught. And if we remember, epsilon naught is 8.85 times 10 to the negative 12. There's units. Should I? Yeah, okay, I'll write the units in here. We'll do our units. And then what is our charge density here? Well, because our charge density, or no, sorry, we're looking at the electric field here. So, oops, I forgot an equal sign here. So since we're looking at the electric field here, and our electric field is pointing downwards, we're going to end up with a minus 150 newtons per coulomb. If you multiply that out, you're going to end up finding a charge density of minus 1.33 times 10 to the minus 9 coulombs per meter squared. Okay, and negative here, we know that it's negative because our electric field is pointing downward, so our electric field lines are terminating at the Earth, not emerging from the Earth, and so this means that the total charge of the Earth, or the charge at the point where that electric field line is terminating, has to be negative, right? So that's sort of our answer for part A. And for part B, what are we looking at? We're looking at the total charge for the Earth, right? And so we know that well, the Earth is basically very, very close to a sphere, and so we know that the surface area of a sphere looks like that. For the Earth, it's going to be 4 pi, and it'll be the radius of the Earth squared. And so we also know that our total Q is going to end up being our charge density at the surface times the surface area. And so we just saw what our charge density at the surface is. Right? And now we need our area, so our area is going to end up being 4 pi, and the radius of the Earth, which we're going to have to square, is going to end up being 6.38 times 10 to the 6 meters, and this all comes squared, right? We can see that the units are going to work out our meter squared here. We're going to cancel our meter squared here. We're going to end up in coulombs, and if you do that calculation, you're going to find that Q is equal to minus 6.8 times 10 to the 5 coulombs, okay? and that's the total charge carried by the Earth. So this is just a nice little example to kind of wrap up the chapter. And so this kind of concludes our work in chapter 22 on electric flux and Gauss's law, and we'll move on from this one. Okay, so I'll see you guys in the next chapter.